power of comparison between methods. Not only that,
but also the spatial distribution. Exactly. Yeah. In fact, the distribution of CDM, the gas in that is you've seen their simulations probably, right? It's 21 centimeter fast cone. They're very diffuse, and so the lines are very spread out. You don't have distinct objects, features in them, because there are filaments there in CDM, but you notice that they've all condensed into tiny little micro galaxies to begin with, and then stars forming them. So you don't have that cold hydrogen reservoir held there like you do with this structure-free smooth filament case.
So you said that there would be, in the wave dark matter case, there would be very deep troughs that comprise that.
Right.
Is that, I missed why.
That's just the filaments that you'd be intersecting the background, and they're cold, or fairly cold. It's this in your expression here.
With redshift, wouldn't it look basically, you're saying because the filaments are discrete and so...
Discrete, yeah. So you need good spatial resolution and good spectral resolution, and then you would see this sort of optical depth of around a few deep dips. But you can change the spin temperature and alter this. You see how to do that there, right? So that would then... It's quite nice because we don't... The length of the filaments and details like that don't matter. What matters here is the average density of the gas, cold gas, at that spin temperature. And the width of the filament, you can trade one for the other. So, we don't expect to know these numbers really very well in advance. We have Toons' simulation as a good guide, but we need now to do our own very detailed simulations. That's a really big job. Cool the gas, put all, not only H2, but also deuterated hydrogen, three-body hydrogen, tritium, and all the rest of it. Then you could get down. But the point is, once you've got to 100 Kelvin by normal molecular cooling, it's not much further to get down to 40 Kelvin. And the gas will keep compressing under the gravity of the filaments. So it should cool more.
I have a question related to the number of families and masses that you need for the actions, because you mentioned two at least.
Well, I think
then
two...
at the end you can have many, as many as you like,
right.
Because then it's not only a one free parameter, you can have many.
Yes, exactly. So that's what string theory is saying, but they're not able to specify the amplitude of each contribution, or even where they are in mass. The only statement they can make, as you might imagine, is that generically there should be a discrete mass spectrum of axions spread over many orders of magnitude. And the proportion in terms of... So we're saying that the dominant dark matter is 10 to the minus 22 eV. And there's maybe if you interpret these central masses in globular clusters, you would infer 10 to the minus 18 eV as a small fraction, about 1 or 2% of the total dark matter. So that's probably good enough to say, well, string theory is not likely to contradict that. It's some kind of generic support for that picture. If there was only one boson that we detect, you could have others. I mean, there's many scenarios that you might think of besides axion-like string theory.
So you need to have more than one, for that scenario.
It would be much more convincing if that was the case.
Final question?
Well, this is going to expose my level of ignorance on the subject, but I do not understand how you came to this 10 to the minus 22 mass for the favorite axion mass from a genes analysis. I don't know what a genes analysis is.
Oh, right, well, he's just...
where these constraints are coming from.
Right, it's a gravitationally self-supporting system, and you consider the projected velocity dispersion of the stars and the projected mass distribution. That's what you normally do with these genes. James Jeans would be the one that wrote expressions for that originally. So I think I have it here.
It's a pressure support of the collapsing of for structure,
Yep.
and it's just a velocity. Anything you have there, the particles or the stars. Or
it's analogous with pressure support in a gas, and that's where Jeans wrote down his famous expression, the Jeans scale, determined by the pressure support and the self-gravity, and that was then. That then I think it was Donald Lyndon Bell, who realised that a stellar system of discrete particles could also be described in terms of a Jeans length, just by analogy with that. So the velocity dispersion is as a function of projected angle is this thing here, and that's one of the measurements. And the other one is the density of the tracer structure of the stars. So you need a number of them, and so you can look at this and say, well, the number of stars is dropping in radius. You measure that, and that gives you then your what you need to solve for the size of the system and its mass, and therefore you get this thing.
That number that you get there, what bounds does it have? I mean, how precise can you say you determine it? Because when I looked at your strain versus mass from the interference between the soliton field and the pulsar frequencies, I saw that it was pretty flat. So in principle, that's going to be difficult to determine from that plot alone.
It might well be, but yes, you're right. Well, the amplitude. Well, the amplitude you would have from that, but the time scale will give you the mass independently of the amplitude. So the amplitude is what we're talking about, the strain, the detectability versus the mass. So actually not as bad as you think, because you would also have, in addition to the strength of the signal, a time scale for the modulation of that signal.
Okay.
That gives you directly the boson mass. So yeah, there's quite a bit of debate about that number, and there are others since who have looked at other dwarf galaxies and tried to make other measurements. We think that we've now got a much better value for this from that other object that I mentioned. It's so extending, because what you really want is a stellar population that extends beyond the soliton scale, and then you can see it. You know, if your stellar population is, as most dwarf spheroidals, unfortunately the case that it's rather central, you only see small numbers of stars in the middle, then you don't have the leverage on that quantity. So this is why we chose this particular object.
yeah, so that mass is derived only from one galaxy.
It's sort of supported by some others that have been looked at since.
It would be nice to
discovered by this long.
Once you determine that mass, then you can make a lot of predictions. Which are for the one single universe that we know. So in principle, that predominant mass, should coincide with many measurements that you make.
That's right. In particular, for many different dwarf galaxies.
Okay.
Right, yes, yeah, they all have to agree.
Okay.
If there's some spectrum of different, that kills the idea.
I think if there is no more question, I think it's time enough to finish this. So thank you very much.